So, almost exactly a year ago at NIPS 2018, David Ha and a co author introduced something called world models. Now, the way that world models work is that they train in three stages. One is that a VAE, a vision model, learns how to encode images from a game environment into a latent representation with only 32 dimensions in the case of a car racing gym in OpenAI and 64 in the case of Doom. Then a MDN RNN is trained on top of that vision model, as well as the actions that somebody takes, and it learns how to predict what the latent space will look like in the future given an action that you take now. Finally, we have a controller, which is trained via evolution to solve the environment given just the latent representation from the VAE and the hidden state from the LSTM. And this works very well in car racing and Doom. It gets state-of-the-art results. Well, I had a simple idea. What if, on top of all of this, I added one thing, which was co-training the VAE with the MDN RNN to pick out the most salient features in an image. Would this give us better quantitative results? Would it give us more interesting qualitative results? I set to find out. So first, just like the original authors, we have to collect data from a bunch of rollouts of each of our gyms, and I have an example of doing that with Doom right here. Then we train, just like the original paper, and if you're like me, you're resource constrained and you can't quite train something that's quite as good as David Ha and co-author's result, but you do end up with something kind of competent, and you can see it driving around in the clip you're watching. But again, what we're really interested in is how the world model's perception of the world changes when we ask it to predict reward while we're training the VAE. And so what you can see here is on the left, we have the actual environment. In the middle, we have its original perception. And on the right, we have the perception that we get when we co-train the two models. And what's kind of interesting here is that it does seem to learn to predict the curve in the road before the curve actually arrives. So that's a new behavior that we get out of this. Now with Doom, you can see that, hey, maybe it's not quite as good at drawing the wall, maybe it's a little bit better at drawing its adversaries, but this seems a little bit less definitive to me. Unfortunately, our quantitative results don't improve. We match the performance, or maybe slightly undershoot it, of the original world model in both cases. However, it's possible that the original latent dimensions of the world model make up for the fact that it's not going to be quite as good at capturing salient features. So a future experiment is to try reducing that dimensionality and seeing if my method improves things.